Hello there, and welcome to the Sleepless Scientist. Tonight, we're turning our gaze towards something ancient and beautiful, stars that have lived for billions of years, stars that are now entering their final chapters, red giants. The life story of a star. Every star has a beginning. It forms from a cloud of gas and dust, collapsing under its own gravity until the pressure and temperature at its core become high enough to ignite fusion. Hydrogen atoms merge, forming helium and releasing energy. That energy pushes outward, balancing the inward pull of gravity. And so the star shines, stable and steady, for billions of years. This is the main sequence, the longest phase of a star's life. Our Sun is a main sequence star right now. It has been for about 4.5 billion years, and it will remain one for another 5 billion more. But nothing lasts forever. Eventually, the hydrogen in the core runs out, the fusion slows, the balance shifts, and the star begins to change. What happens next depends on the star's mass. For stars like our Sun, the transformation is gradual, elegant, and ultimately beautiful. They become red giants, massive, luminous, and glowing with a soft, ancient light. This is their story. The moment a star begins to change. For billions of years, a star burns hydrogen in its core. The process is steady, reliable, almost eternal. But the core is finite. Eventually, the hydrogen runs low. The fusion reactions slow down, and the energy pushing outward begins to weaken. Without that outward pressure, gravity takes over. The core begins to contract. Odd as it shrinks, it heats up. The temperature rises, and something unexpected happens. The hydrogen surrounding the core, which was too cool to fuse before, suddenly becomes hot enough. A shell of hydrogen around the inert helium core ignites. Fusion begins again, but this time in a thin layer rather than throughout the core. This shell burning produces even more energy than the star generated during its main sequence life. That energy pushes outward with tremendous force. The outer layers of the star begin to expand, slowly at first, then faster. The star swells, it cools, and it transforms into a red giant. The moment of change is quiet, but its consequences are profound. The end of hydrogen in the core. A star's core is where the magic happens. Hydrogen fuses into helium, releasing energy in the form of light and heat. This process powers the star for most of its life. But the core is only so large, and the hydrogen supply is limited. As billions of years pass, the hydrogen in the core is gradually consumed. Helium ash accumulates, the byproduct of countless fusion reactions. Helium doesn't fuse easily. It requires much higher temperatures than hydrogen. So as the hydrogen runs out, the helium just sits there, inert and growing. The core becomes a ball of helium, surrounded by a shell of remaining hydrogen. Fusion in the core stops. The star's energy source shuts down. For a brief moment, the core is quiet, but that quiet doesn't last. Gravity is patient, and without the outward pressure of fusion, the core begins to collapse. It shrinks, heating up as it compresses, and that heat will soon trigger the next phase of the star's evolution, the collapse that starts expansion. It seems paradoxical. The core collapses, and the star expands. But that's exactly what happens. As the helium core contracts under gravity, it heats up. The surrounding hydrogen, which was previously too cool to fuse, suddenly finds itself in a much hotter environment. The temperature rises above the threshold needed for fusion, and so a shell of hydrogen around the core ignites. This hydrogen shell burning is incredibly efficient. It produces more energy than the core ever did during the main sequence. That energy has to go somewhere. It pushes outward against the star's outer layers. Those layers begin to expand. They swell outward, moving farther and farther from the core. As they expand, they cool. The surface temperature drops. The color shifts from yellow or white to orange, and then red. The star becomes larger, cooler, and more luminous. It becomes a red giant. The collapse of the core triggers the expansion of the envelope. It's one of the beautiful ironies of stellar physics. Death at the center brings transformation to the whole. The birth of a red giant. The transformation is complete. The star, once small and hot, is now enormous and cool. Its outer layers have expanded to hundreds of times their original size. The surface temperature has dropped from several thousand degrees to only a few thousand. The color has shifted to red. The star is now a red giant. From a distance, it's breathtaking. A massive glowing sphere of red and orange light. Its luminosity has increased dramatically. Even though its surface is cooler, its size makes it incredibly bright. A red giant can shine thousands of times more brightly than it did during its main sequence life. The star has entered a new phase. It's no longer young, no longer stable. It's aging, evolving, transforming, and it will continue to change until it reaches the end of its life. But for now, it glows. A beacon in the darkness. A star that has lived long enough to become something beautiful and strange. A red giant, burning quietly in the depths of space. The star that grows 1,000 times larger. The scale of a red giant is difficult to comprehend. A star that was once similar in size to our sun can expand to a radius hundreds, even thousands of times larger. If our sun were to become a red giant today and expand to its predicted maximum size, it would reach beyond the orbit of Mars. Mercury would be swallowed. Venus would be consumed. Earth might be engulfed, or it might barely survive at the edge of the expanding envelope. The outer layers of a red giant are tenuous. They're more like a diffuse atmosphere than solid material. The density is so low that by Earth standards, it's almost a vacuum. Yet the star's gravitational pull holds these layers together. The expansion is driven by the immense energy output from the hydrogen shell burning around the core. That energy pushes outward with relentless force, and the star responds by growing, swelling, becoming a giant in every sense of the word. It's a transformation that takes millions of years, but once complete, the star is almost unrecognizable from what it once was. The cooling of its outer layers. As a star expands into a red giant, its outer layers move farther and farther from the core. And as they move outward, they cool. The surface temperature drops. A main sequence star like our sun has a surface temperature of about 5,800 Kelvin. But when it becomes a red giant, that temperature can drop to 3,000 Kelvin or lower. The cooling happens because the same amount of energy is being spread over a much larger area. The surface area of the star increases dramatically, and while the total energy output might be higher, the energy per unit area is much lower. The result is a cooler surface. The color changes as a consequence of this cooling. Hot stars are blue or white. Cooler stars are yellow or orange. And the coolest stars, like red giants, are red. The outer layers glow with a soft, warm light. It's the light of a star that has aged, a star that has seen billions of years pass, and a star that is now entering the final stages of its life. The transformation into a crimson sun, the color of a red giant, is unmistakable. Deep red, sometimes tinged with orange or even brown. It's the color of cooling embers, of sunset, of something fading, but still beautiful. The color comes from the low surface temperature. Wien's law tells us that the wavelength of light a star emits depends on its temperature. Hot stars emit shorter wavelengths, blue and ultraviolet light. Cool stars emit longer wavelengths, red and infrared. A red giant is cool enough that most of its light is in the red part of the spectrum. Some red giants are so cool that they emit more infrared radiation than visible light. They're almost invisible to our eyes, but they shine brightly in infrared telescopes. The transformation from a bright yellow sun to a crimson giant is one of the most dramatic changes a star can undergo. It's a visual reminder that the star has changed, that it's no longer what it was, that it's moving toward the end. And yet in that crimson glow, there's a kind of beauty, the beauty of age, of transformation, of light that persists, even as the star fades. The balance between gravity and pressure. Throughout a star's life, two forces are constantly at war. Gravity pulls inward, trying to collapse the star. Pressure pushes outward, trying to expand it. The balance between these forces determines the star's size, temperature, and stability. During the main sequence, the balance is perfect. Fusion in the core generates enough pressure to counteract gravity. The star is stable. But when the star becomes a red giant, the balance shifts. Hydrogen shell burning produces enormous amounts of energy. That energy creates pressure in the outer layers, pushing them outward. Gravity tries to pull them back, but it's fighting a losing battle. The outer layers expand. Meanwhile, the core is collapsing under gravity, with no fusion to support it. The helium core contracts, becoming denser and hotter. The core shrinks, while the envelope expands. Two opposite processes happening at the same time. This new balance is less stable than before. The star pulsates, swells, and sheds mass. It's a dynamic, evolving system, and it won't last forever. The glow of hydrogen shell burning. The engine that powers a red giant is different from what powered it before. During the main sequence, fusion happened in the core, but in a red giant, the core is inert. Fusion happens in a shell around the core, a thin layer where hydrogen fuses into helium. This hydrogen shell burning is incredibly efficient. The temperatures and pressures in the shell are higher than they ever were in the core. During the main sequence, the fusion rate is faster. The energy output is greater. That's why red giants are so luminous. Even though their surfaces are cool, they shine brightly because they're producing so much energy. The shell gradually works its way outward as it consumes the hydrogen around it. As time passes, the shell moves to larger and larger radii, and the helium core grows, accumulating the ash from the shell burning. Eventually, the core will become hot and dense enough for something new to happen. But for now, the hydrogen shell burns steadily, powering the giant and keeping it luminous across the galaxy. The layers of fusion. Inside the giant, a red giant is not a uniform ball of gas. It's layered, like an onion. At the very center is the inert helium core. No fusion happening here, just helium atoms packed tightly together, compressed by gravity. Surrounding the core is the hydrogen-burning shell. This is where fusion occurs, where hydrogen atoms merge to form helium and release energy. Outside the shell is the vast envelope, layers upon layers of hydrogen and helium, expanding outward from the core. This envelope is enormous. It makes up most of the star's volume, but it contains only a small fraction of the star's mass. The envelope is cool and diffuse. The temperature drops as you move outward, from thousands of degrees near the shell to only a few thousand at the surface. The structure is delicate. The envelope is loosely bound to the core, and over time, it will be lost, shed into space by stellar winds. But for now, it remains a glowing, layered sphere, a star in transition, revealing its inner structure through the light it emits. The core that shrinks, while the star expands. One of the most fascinating aspects of red giant evolution is this paradox. The core shrinks, while the star expands. As the helium core loses its internal pressure, gravity compresses it. It becomes smaller, denser, and hotter. The core is collapsing. Meanwhile, the outer layers are expanding, driven outward by the energy from hydrogen shell burning. They swell to enormous sizes. The star grows. Two opposite processes happening simultaneously. The core contracts. The envelope expands. It's a consequence of how stars respond to changes in energy production. The shell burning produces more energy then the star can easily radiate away. That excess energy inflates the outer layers, but without fusion in the core, there's nothing to support it against gravity, so it collapses. This dual process will continue until the core reaches a critical point. When the temperature and density become high enough, helium fusion will ignite, and the star will enter a new phase. But until then, the core shrinks, and the star grows. The beauty of slow stellar aging. There's something poetic about watching a star age. It happens on timescales far beyond human comprehension. Millions of years, tens of millions, hundreds of millions. We can't watch a single star transform in real time, but we can observe many stars at different stages of their lives. And from those observations, we can piece together the story. A star begins its life hot and bright. It settles into a long, stable middle age, and then slowly it begins to change. It swells, it cools, it transforms into something new. The beauty of stellar aging is in its inevitability. Every star will age, every star will change, and in that change, there's a kind of grace. The red giant phase is not a failure. It's not a sign that the star is broken. It's just the next chapter, a natural part of the cycle, and in its own way, it's just as beautiful as the star's youth, perhaps more so, because it's a reminder that even the longest lives eventually come to an end. The color that comes with time. Color is one of the most obvious signs of a star's age and temperature. Young stars are hot. They burn bright blue or white. Middle-aged stars, like our sun, are yellow, and old stars, red giants, glow in shades of red and orange. The color shift is a direct result of cooling. As the star expands, its surface temperature drops, and as the temperature drops, the wavelength of emitted light increases. Blue light requires high temperatures. Red light can be produced at much lower temperatures. The color of a red giant is the color of age. It's warm, soft, and inviting in a way that blue stars never are. There's a gentleness to red light, a calm. Looking up at a red giant in the night sky, you're seeing a star that has lived for billions of years. A star that has burned through most of its fuel. A star that is nearing the end. And that red glow is its signature, a mark of time, a color that only comes with age. The deep red of cooling light. The red light of a giant star is not harsh. It's not bright in the way young stars are bright. It's a soft, diffuse glow, the kind of light that fills a room at sunset, the kind of light that feels warm even though the star itself is cooling. Red giants emit most of their energy in the infrared part of the spectrum, wavelengths longer than red light, wavelengths we can't see with our eyes, but we can feel them as heat. In infrared, red giants are incredibly bright. They glow with a warmth that belies their distance. Astronomers use infrared telescopes to study red giants because so much of their light is hidden from visible wavelengths. These telescopes reveal details that would otherwise be invisible. Dust shells, mass loss, structures in the outer envelope. The deep red of a red giant is more than just a color. It's a window into the star's physics, a clue to its temperature, its size, and its evolutionary state. And it's beautiful. A reminder that not all starlight is blazing and fierce. Some is gentle, calm, and just as powerful in its own way. The star's surface, growing cold yet bright. Here's a contradiction. A red giant's surface is cooler than it was during the main sequence, and yet the star is brighter. How is that possible? The answer lies in size. The red giant's surface temperature might be only half what it was before, but the surface area has increased by thousands of times, and brightness depends on both temperature and surface area. A cool, large star can be much brighter than a hot, small star. Red giants are among the most luminous stars in the galaxy. Some shine with the light of thousands, even tens of thousands of suns. They're visible across enormous distances, beacons in the night. The cold surface is still radiating energy, lots of energy, just at longer wavelengths. And because the star is so large, even a relatively low energy output per unit area adds up to an enormous total luminosity. It's counterintuitive, but it's one of the fundamental lessons of stellar physics. Size matters, and in the case of red giants, size makes them some of the brightest objects in the sky. The soft light seen across the galaxy. Red giants are visible from far away. Their immense luminosity makes them stand out, even in crowded star fields. When we look at other galaxies, red giants are among the stars we can pick out individually. Their soft, red light is distinctive. It cuts through the glare of younger, hotter stars, and it tells a story. The story of age, of transformation, of stars nearing the end of their lives. In our own galaxy, red giants are scattered throughout the sky. Some are famous: Betelgeuse, Antares, Arcturus. Others are fainter, less well known, but they're all following the same path. They've all left the main sequence. They've all expanded and cooled, and they're all shining with that characteristic red light. When you look up at a red giant, you're seeing light that has traveled for years, decades, even centuries. Light that left the star when it was already ancient. And that light carries information about the star's temperature, its size, its composition. The soft light of red giants is more than just beautiful. It's informative, a message from the distant past, a glimpse into the future of every sun-like star. The end of main sequence life. The main sequence is a star's prime, the period of stability and steady burning. It's the longest phase of a star's life, lasting billions of years. But it doesn't last forever. Eventually, the hydrogen in the core runs out. Fusion slows. The core contracts, and the star leaves the main sequence. The transition is gradual. The star doesn't suddenly jump from one phase to another. It slowly evolves, expanding and cooling over millions of years. Astronomers classify stars by their spectral type and luminosity class. Main sequence stars are class V. Giants are class 3. Supergiants are class I. As a star evolves off the main sequence, it moves from class V to class 3. It becomes a giant. The end of the main sequence is not the end of the star. It's just the end of one chapter. The star still has millions, even hundreds of millions of years ahead of it. But it's a different kind of life now. Less stable, more dynamic, and ultimately leading toward the final phase. The end of main sequence life is the beginning of something new, the beginning of the red giant phase. The moment a star becomes elderly. There's no precise moment when a star becomes old. It's a gradual process. But there is a turning point. The moment when the hydrogen in the core is exhausted, when fusion stops at the center, when the core begins to contract. That's the moment when the star's youth ends and its old age begins. It's not dramatic. There's no explosion, no sudden change. The star just keeps shining. But inside, everything is different. The energy source has shifted from the core to a shell. The structure has changed from a simple, homogeneous ball to a layered, complex object. The star is now elderly. It's lived most of its life. It's consumed most of its fuel, and it's entering the final stages. But elderly doesn't mean weak. Red giants are some of the most luminous stars in the galaxy. They're powerful, dynamic, and beautiful. Aging, yes, but still shining, still contributing to the cosmos. The moment a star becomes elderly is not the end. It's a transition, a transformation, a new beginning, in a way, the beginning of the end. The swelling that consumes its inner planets. As a star expands into a red giant, its outer layers reach outward. They grow larger and larger, eventually extending far beyond the star's original size. For stars with planetary systems, this expansion has consequences. The inner planets, those orbiting close to the star, are in danger. As the star swells, it can reach their orbits, and when it does, they're consumed, swallowed by the expanding envelope. Engulfed in the star's outer layers, the planet doesn't survive. It spirals inward, heated by friction with the star's atmosphere. Eventually, it plunges into the deeper, hotter layers, and it's destroyed, vaporized, turned into gas and absorbed into the star. This is the fate that awaits many inner planets around red giants. Rocky worlds, once bathed in comfortable warmth, find themselves inside their star. It's a violent end, but it's also an inevitable one. The star's expansion is driven by physics, by the energy from hydrogen shell burning, and there's nothing the planet can do to stop it. It's a reminder that planetary systems are not eternal. They evolve, just like the stars they orbit. The fate of planetary systems around red giants. Not all planets are doomed when their star becomes a red giant. Outer planets, those orbiting farther from the star, may survive. They'll be heated, certainly. Their surfaces will warm, icy moons might melt, atmospheres might change, but they won't be consumed. In fact, the increased luminosity of the red giant might even make these outer worlds more habitable, at least temporarily. Frozen moons could become warm enough for liquid water. Distant planets could enjoy a brief spring, but it's only temporary. The red giant phase doesn't last forever, and when it ends, the star will shed its outer layers, leaving behind a white dwarf. The planets will cool again, returning to their frozen state, or they might be disturbed by the mass loss, their orbits becoming unstable. Some might be ejected entirely, flung out into interstellar space. The fate of a planetary system around a red giant is complex. Some worlds are destroyed, others are transformed, and a few might survive, scarred but intact, orbiting a dead star in the darkness. The orbits that slowly decay. Even if a planet isn't immediately swallowed by a red giant, it's not safe. The star's expansion changes the gravitational environment. The outer layers of the red giant are diffuse, but they're not empty. As a planet orbits through this material, it experiences drag friction. The drag slows the planet down, and as it slows, its orbit decays. It spirals inward. The process is slow. It takes thousands, even millions of years, but it's relentless. With each orbit, the planet loses energy. It drifts closer to the star. Eventually, it crosses into the denser inner regions of the envelope. The drag increases, the spiral accelerates, and the planet is lost. This orbital decay has been observed in some systems. Planets on tight orbits around evolved stars. Planets that are slowly being consumed. It's a gentle death, in a way, not a sudden catastrophe, but a slow fade, a gradual descent into the heart of the star, and a reminder that even the most stable orbits are subject to change over time. The inevitable death of inner worlds. For planets orbiting close to their stars, the red giant phase is a death sentence. There's no escape, no way to avoid the expanding envelope. The planet might survive for a while, orbiting just beyond the star's edge, but eventually, the star will reach it. The planet will be enveloped, and it will be destroyed. This is what awaits Mercury and Venus. When our sun becomes a red giant, Mercury, closest to the sun, will be the first to go. It will be swallowed as the sun expands beyond its orbit. Venus will follow shortly after. Both planets will spiral inward, heated to thousands of degrees, and eventually vaporized. Earth's fate is less certain. The sun might expand to Earth's orbit, or it might not. But even if Earth avoids being swallowed, it won't survive unscathed. The heat will be intense. The oceans will boil away. The atmosphere will be stripped. Earth will become a barren, lifeless rock. The inevitable death of inner worlds is a somber reminder. Everything has an end, even planets, even Earth. The transformation of solar systems. When a star becomes a red giant, everything changes. The star itself transforms, swelling and cooling, but the planets change too. Inner planets are consumed or scorched. Outer planets are warmed. Moons that were frozen for billions of years suddenly find themselves in a new environment. The entire system is transformed. The star's mass loss also affects the planets. As the star sheds its outer layers, it loses mass, and as it loses mass, its gravitational pull weakens. The planets respond by moving to larger orbits. They drift outward, no longer held as tightly. Some might escape entirely, becoming rogue planets wandering through interstellar space. The transformation of a solar system during the red giant phase is dramatic. It's a time of upheaval, of change, of endings and new beginnings. The system that emerges is very different from the one that existed before. Fewer planets, altered orbits, a dying star at the center. It's the twilight of a solar system, the final chapter before the star fades away. The future of our own sun. Our sun is a middle-aged star. It's about 4.6 billion years old, and it has about 5 billion years left before it runs out of hydrogen in its core. When that happens, the sun will begin its transformation into a red giant. The process will take millions of years. The sun will expand slowly, at first, then more rapidly. Its outer layers will reach beyond Mercury's orbit, possibly beyond Venus's, maybe even as far as Earth. The sun's luminosity will increase. It will become thousands of times brighter than it is now. The inner planets will be heated to extreme temperatures. Earth's surface will become uninhabitable long before the sun actually reaches us. The oceans will evaporate. The atmosphere will be lost. Life, if it still exists, will have to find shelter elsewhere. Eventually, the sun will shed its outer layers, creating a planetary nebula, and at the center will be a white dwarf, the cooling remnant of the sun's core. This is the future, not tomorrow, not in 1,000 years, but billions of years from now. The sun's red giant phase is inevitable, and when it comes, everything will change. The prediction of its red giant phase. Scientists have modeled the sun's future evolution in great detail. They use what we know about stellar physics, the sun's mass, and its composition to predict how it will change over time. The predictions are remarkably precise. In about 5 billion years, the sun will exhaust the hydrogen in its core. It will begin to expand, entering the red giant phase. Over the next billion years or so, the sun will grow to about 250 times its current radius. Its surface temperature will drop to around 3000 Kelvin, and its luminosity will increase by thousands of times. The sun will remain a red giant for several 100 million years. During this time, it will fuse helium in its core, creating carbon and oxygen. Eventually, it will shed its outer layers and become a white dwarf. These predictions are based on solid physics. They're not speculation. We've observed thousands of stars at various stages of evolution, and the patterns are clear. The sun's future is written in the stars we see around us. Stars that are already red giants. Stars that show us what's to come. The Earth's final days, beneath a dying sun. Long before the sun becomes a red giant, Earth will become uninhabitable. As the sun ages, it's gradually increasing in brightness. This is a natural consequence of stellar evolution. The sun is already about 30% brighter than it was when it formed, and it will continue to brighten. In about 1 billion years, the sun will be bright enough that Earth's oceans will begin to evaporate. The water vapor will trap heat, creating a runaway greenhouse effect. Temperatures will soar, the oceans will boil away, and Earth will become a Venus-like world, hot and barren. By the time the sun actually becomes a red giant, billions of years from now, Earth will have been lifeless for eons. The planet might still exist, a scorched rock orbiting close to the expanding sun, or it might be consumed, swallowed by the sun's outer layers. Either way, Earth's story will be over. The final days beneath a dying sun will be a slow fade, a gradual loss of everything that made Earth habitable. It's a somber thought, but it's also far in the future. The sky that will glow red. One day, imagine standing on Earth, billions of years in the future. The sun has become a red giant. It fills the sky, enormous and crimson. It no longer looks like the sun we know. It's a massive, glowing sphere, hundreds of times larger. Its light is red and warm. The sky itself glows with that red light, casting everything in shades of orange and crimson. There's no blue sky anymore. No white clouds, just red. The heat is unbearable. The surface is molten rock, a sea of lava. The atmosphere, if it still exists, is thin and scorching. Nothing lives here. Nothing can. This is Earth's final phase, the last days under a dying sun. Of course, no one will be there to see it. Humanity, if it still exists, will have left long ago, migrated to other worlds, other star systems. But Earth will remain, locked in orbit, bathed in red light, a silent witness to the sun's transformation. The sky that will glow red one day is a vision of the far future, a reminder that even our home world has an expiration date. The sun, expanding beyond Mercury's orbit. When the sun becomes a red giant, it will expand dramatically. Current models predict it will reach a radius of about 1.2 astronomical units. That's beyond Mercury's orbit, which is at 0.39 AU, and close to, or possibly beyond, Venus's orbit at 0.72 AU. Mercury will be consumed. There's no doubt about that. The sun's outer layers will reach Mercury's orbit, and the planet will be engulfed. It will spiral inward through the sun's atmosphere, heating up and eventually disintegrating. Venus might suffer the same fate. The predictions are less certain for Venus. It depends on exactly how large the sun becomes, and on how much mass the sun loses during its expansion. Mass loss will weaken the sun's gravity, allowing the planets to drift outward slightly. But it might not be enough to save Venus. Earth's fate is even more uncertain. The sun might reach Earth's orbit, or it might not. We're right on the edge. But even if Earth avoids being swallowed, it won't survive in any meaningful way. The sun's expansion is a death sentence for the inner solar system, the oceans that will boil away. Long before the sun expands to Earth's orbit, the oceans will be gone. As the sun brightens over the next billion years, Earth will heat up, slowly at first, then more rapidly. The increased heat will cause more evaporation. Water vapor is a greenhouse gas. It traps heat, and as more water enters the atmosphere, the temperature rises further. It's a feedback loop, a runaway greenhouse effect. Eventually, the oceans will begin to boil, not all at once, but gradually, over millions of years. The water vapor will rise into the upper atmosphere, where ultraviolet light from the sun will break it apart. Hydrogen will escape into space. Oxygen will be lost or locked into rocks, and the oceans will disappear. By the time the sun becomes a red giant, Earth will be a dry, barren world. No water, no life, just rock and dust, baked under a red sky. The loss of the oceans is one of the most poignant aspects of Earth's far future. Water is what makes Earth special, and when it's gone, Earth becomes just another dead planet. The final breath of our home star. The sun will not end as a red giant. The red giant phase is just one step in its death. After the sun expands and fuses helium in its core, it will begin to lose mass. Stellar winds will carry away the outer layers. The envelope will be shed, blown into space by radiation pressure and pulsations. What's left behind will be the core, a hot, dense ball of carbon and oxygen, about the size of Earth. This is a white dwarf. The final breath of the sun will be the creation of a planetary nebula. The shed material will glow, illuminated by ultraviolet light from the white dwarf. It will spread outward, forming a beautiful, expanding shell. For thousands of years, the nebula will shine, and then it will fade, dispersing into the interstellar medium. The white dwarf will remain. It will cool slowly over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. But by then, the universe itself will be unimaginably old. The sun's final breath is far in the future, but it's coming, inevitable and serene. The timescale of stellar evolution. Stellar evolution happens on timescales that are difficult for humans to grasp. A star like the Sun spends about 10 billion years on the main sequence, 10 billion years of stable hydrogen burning. Then it spends a few 100 million years as a red giant, a brief phase by comparison. Then perhaps another 100 million years, fusing helium. And then it ends, shedding its outer layers and becoming a white dwarf. The entire process, from birth to death, takes about 10 to 12 billion years. That's twice the current age of the universe. Well, not quite, but you get the idea. It's a long time. These timescales are why we can't watch a single star evolve. We can only observe snapshots, stars at different stages. But from those snapshots, we can piece together the story. We can understand the sequence of events, and we can predict the future. Stellar evolution is slow, patient, inevitable, and beautiful in its own way. A reminder that the universe operates on timescales far beyond our own. The billions of years leading to this. A star doesn't become a red giant overnight. It takes billions of years of preparation, billions of years of steady burning, fusing hydrogen into helium, slowly accumulating helium ash in the core. The process is gradual, imperceptible from day to day, year to year, even century to century. But over millions and billions of years, the changes add up. The core becomes more helium-rich. The temperature and pressure shift, the balance changes, and eventually, the hydrogen runs out. All those billions of years were leading to this moment. The moment when the star transforms, when it leaves the main sequence and becomes a giant. It's the culmination of a long life, the product of countless fusion reactions, trillions upon trillions of them, each one adding a tiny bit of helium to the core, each one bringing the star one step closer to its transformation. The billions of years leading to the red giant phase are not wasted. They're the star's prime, its productive years, the time when it shines steadily, providing light and warmth to any planets that might orbit it. But they're also finite, and when they end, the star must change, must evolve, must become something new. The quiet burning of helium ash. After billions of years of hydrogen fusion, the core of a star becomes a ball of helium. This helium is the ash of hydrogen burning, the waste product, if you will. But helium isn't truly waste. It's fuel, just fuel, that requires higher temperatures to burn. During the early red giant phase, this helium core is inert. It sits at the center, compressed by gravity, but not fusing. It's too cool. Helium fusion requires temperatures of about 100 million Kelvin, much hotter than hydrogen fusion. So the helium waits. As the core contracts under gravity, it heats up, slowly, steadily. The temperature rises, and eventually, it reaches the threshold. The helium ignites. Helium atoms begin to fuse. 3 helium nuclei combine to form carbon. Sometimes a 4th helium nucleus joins, creating oxygen. The core comes alive again. Fusion resumes, and the star stabilizes, at least for a while. The quiet burning of helium ash is the second major phase of fusion in a star's life. It's briefer than hydrogen burning, but it's no less important. The beginning of helium fusion. When helium fusion begins, it's a significant moment. The star has been in a state of instability, with only shell burning to support it. But now, fusion resumes in the core. The star settles into a new equilibrium. For stars like the Sun, The beginning of helium fusion is dramatic. It happens suddenly, in what's called a helium flash. We'll talk more about that in a moment. For more massive stars, the transition is smoother. The core gradually heats up until helium fusion begins. There's no flash, just a steady ignition. Either way, helium fusion changes the star. The core is now producing energy again. The pressure from that energy pushes back against gravity. The core stops contracting. It might even expand slightly, and the star's outer layers respond. They contract a bit, becoming hotter and more compact. The star moves to a different part of the Hertzsprung-Russell diagram. It's still a giant, but it's a different kind of giant now. More stable, less variable, and it will remain in this phase for tens to hundreds of millions of years, burning helium in its core. The helium flash, a sudden awakening. For stars with masses similar to the Sun, the beginning of helium fusion is violent. As the helium core contracts, it becomes degenerate. That's a quantum mechanical state, where the electrons are packed so tightly that they resist further compression through a pressure that doesn't depend on temperature. In a degenerate core, temperature can rise without causing expansion, and that's dangerous. When the temperature finally reaches 100 million Kelvin, helium fusion ignites. But because the core is degenerate, it can't expand to regulate the temperature. The fusion rate skyrockets. Energy floods the core. It's a runaway reaction. This is the helium flash. For a few seconds, the core produces as much energy as the entire galaxy, but almost all of that energy goes into lifting the degeneracy. The core expands, the pressure becomes normal again, and the fusion stabilizes. The helium flash sounds dramatic, and in terms of energy, it is, but it happens deep inside the star. The outer layers don't even notice. There's no visible change. From the outside, the star looks the same, but inside, everything has changed. The core that ignites in a moment. The helium flash happens quickly. The runaway fusion lasts only a few seconds. In that brief moment, the core transitions from a degenerate, inert state to an active, fusing state. The energy released is staggering, but it's not catastrophic. The star doesn't explode. The energy heats the core, lifting it out of degeneracy. The core expands, and the fusion rate drops to a sustainable level. After the flash, the star settles into a stable phase of helium burning. The core fuses helium into carbon and oxygen, and the star can relax. The moment of ignition is a turning point. It marks the beginning of the star's final fuel source. After helium is exhausted, stars like the Sun have nothing left to burn. They'll shed their outer layers and become white dwarfs. But for now, the star has a reprieve. A few 100 million more years of fusion, a few 100 million more years of light. The core that ignites in a moment gives the star a second life. Brief, but meaningful. The triple alpha process inside. Helium fusion is different from hydrogen fusion. It's more complex, and it requires a clever trick of nuclear physics. Helium nuclei are also called alpha particles, and helium fusion is called the triple alpha process. Here's how it works. Two helium nuclei collide and fuse, forming beryllium-8. But beryllium-8 is unstable. It decays almost immediately, breaking back into two helium nuclei. The reaction seems pointless, but if a third helium nucleus collides with the beryllium-8 before it decays, something remarkable happens. The three helium nuclei fuse into carbon-12. It's a three-body reaction. Three particles have to come together at the same time. That's incredibly rare, but in the core of a red giant, where the density and temperature are high enough, it happens billions of times per second. Sometimes, a fourth helium nucleus fuses with the carbon, creating oxygen-16. The triple alpha process is how stars create carbon and oxygen, the elements essential for life. Without this process, we wouldn't exist. It's one of the most important reactions in the universe. The creation of carbon and oxygen. Carbon and oxygen are everywhere, in rocks, in water, in the air we breathe, in our bodies. Every atom of carbon and oxygen in your body was created inside a star. Most of it was created in red giants through helium fusion. The triple alpha process builds carbon, and further helium capture builds oxygen. These elements are forged in the cores of dying stars. When the star eventually sheds its outer layers, the carbon and oxygen are released into space. They join the interstellar medium. They become part of new clouds of gas and dust, and eventually, they're incorporated into new stars, new planets, new life. Red giants are element factories. They take simple helium and turn it into the building blocks of complexity. Without red giants, the universe would be a much simpler place. Just hydrogen and helium. No planets, no life, no us. The creation of carbon and oxygen in red giant cores is one of the most important processes in cosmic evolution. It's how the universe becomes rich and diverse, how it becomes interesting. The star's heart becomes an element factory. The core of a red giant is where the magic happens. It's where helium fuses into carbon and oxygen, where the elements of life are born. But it doesn't stop there. In more massive red giants, those with several times the sun's mass, the process continues. After helium is exhausted, the core contracts again. It heats up, and if the star is massive enough, it can ignite carbon fusion. Carbon fuses into neon and magnesium. The neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron. Each stage produces heavier elements. Each stage happens faster than the last. Carbon burning lasts thousands of years. Oxygen burning lasts months. Silicon burning lasts days. The star's heart becomes a multi-layered element factory, each layer fusing different elements, building the periodic table, one reaction at a time. For stars like the Sun, the process stops at carbon and oxygen, but for massive stars, it continues all the way to iron. And that's when things get interesting. The layers like the rings of an onion. A massive red giant has a structure like an onion, layers upon layers, each one fusing different elements. At the very center is an iron core. No fusion happening here. Iron is the end of the line. Outside the iron core is a silicon burning shell, then an oxygen burning shell, then neon, carbon, helium, and hydrogen shells. Each layer is hotter than the one outside it, and each is producing energy through fusion. It's a complex, multi-layered system, and it's unstable. The star is producing energy at an enormous rate, but it's also losing mass through stellar winds. The outer layers are barely bound to the star, and the core is growing heavier with each passing moment. This onion layer structure is the final stage before a supernova. When the iron core becomes too massive, it will collapse, and the star will explode. But for stars like the Sun, the structure is simpler, just a carbon-oxygen core surrounded by a helium-burning shell and a hydrogen-burning shell. And eventually, the outer layers will be shed, leaving the core behind. The fusion zones within the giant. Inside a red giant, fusion doesn't happen everywhere. It's confined to specific zones, thin shells where the temperature and pressure are just right. In the helium-burning phase, there's a helium fusion zone in the core, and there's often still a hydrogen-burning shell farther out. The region between the shells is inert, no fusion, just layers of helium or carbon, sitting quietly. The fusion zones are where the action is, where nuclei collide and merge, where energy is released. The energy flows outward through the inert layers, eventually reaching the surface. By the time it reaches the surface, it's been transformed. High-energy gamma rays from the fusion zone become visible in infrared light at the surface. The journey takes thousands of years. Photons bounce around inside the star, gradually losing energy with each interaction. The fusion zones are the heart of the star. Without them, the star would collapse. They're what keeps the giant alive, And when they finally shut down, the star's life is over. The outer envelope, expanding into space. The outer envelope of a red giant is loosely bound. It's held to the star by gravity, but just barely. The envelope is enormous, diffuse and cool, and it's unstable. Stellar winds carry material away from the surface, slowly at first, but as the star ages, the mass loss accelerates. The winds are driven by radiation pressure. Light from the core pushes on dust particles in the outer atmosphere. Those particles drag gas with them, and the gas flows outward, escaping the star's gravity. Over time, the envelope is gradually stripped away. Layer by layer, the star loses mass. The envelope expands into space, forming a cloud around the star. This cloud is the beginning of a planetary nebula, but we're not there yet. For now, the envelope is still mostly intact, still glowing, still part of the star. But it's expanding, slowly dissolving into the darkness. The outer envelope is the star's future, the material that will someday form a nebula and enrich the galaxy with elements forged in the star's core. The slow loss of stellar mass. Red giants are leaky. They're constantly losing mass through stellar winds. For a star like the Sun in its red giant phase, the mass loss rate might be about 1/10,000,000th of a solar mass per year. That doesn't sound like much, but over millions of years, it adds up. By the time the Sun finishes its red giant phase, it will have lost about 30 to 40% of its mass. That material doesn't disappear. It forms a shell around the star, a slowly expanding cloud of gas and dust. The mass loss has consequences. As the star loses mass, its gravitational pull weakens. Planets in orbit drift outward. The outer layers become even more loosely bound, and the star becomes more unstable. Eventually, the mass loss accelerates. The star begins to pulsate, and in a relatively short time, the entire envelope is shed. The slow loss of stellar mass is a natural part of red giant evolution. It's how the star prepares for its final transformation, and how it returns material to the galaxy, enriching it with the elements created during fusion, the winds that carry away a star's life. Stellar winds are streams of particles flowing away from a star. All stars have winds. Even the Sun has one, called the solar wind. But red giant winds are much stronger. The winds are driven by radiation pressure and pulsations. As the star pulsates, it expands and contracts. During expansion, the outer layers move outward, and some of that material has enough velocity to escape. The winds carry away not just hydrogen and helium, but also heavier elements: carbon, oxygen, nitrogen, elements created through fusion in the star's core. These elements mix into the interstellar medium. They become part of the raw material for new stars and planets. The winds are how a star returns its life to the galaxy. Everything it created, everything it fused in its core, is carried away on the winds, scattered into space, waiting to be used again. The winds that carry away a star's life are both an ending and a beginning. They mark the star's death, but they also seed the galaxy with the ingredients for new life. The nebula forming from its own material. As a red giant loses mass, that material doesn't just vanish. It forms a cloud around the star, an expanding shell of gas and dust. This is the beginning of a planetary nebula. Though the name is misleading, it has nothing to do with planets. The nebula is made of the star's outer layers, material that was once part of the star's atmosphere. Now it's drifting away, illuminated by the hot core at the center. The nebula is beautiful, glowing in shades of red, green, and blue. Each color corresponds to a different element. Hydrogen glows red, oxygen glows green. The core, now a white dwarf, emits ultraviolet light that ionizes the gas, and the ionized gas glows. The nebula will expand for thousands of years. Eventually, it will disperse into the interstellar medium. But for a brief time, it's one of the most beautiful objects in the sky, a monument to the star that created it. a reminder that even in death, stars create beauty. The start of planetary nebula creation. The creation of a planetary nebula begins during the red giant phase. As the star loses mass through winds, a shell of material accumulates around it. When the star finally exhausts its fuel and sheds its envelope, that shell is illuminated. The hot core, now exposed, emits intense ultraviolet radiation. That radiation ionizes the surrounding gas, and the gas glows. The result is a planetary nebula, a luminous shell surrounding a fading star. The process is relatively quick by astronomical standards. The nebula lasts for about 10,000 to 20,000 years before it disperses. But during that time, it's spectacular. Planetary nebula come in many shapes. Some are spherical, others are bipolar, with two lobes extending in opposite directions. Still others are irregular, chaotic. The shapes are determined by the star's rotation, magnetic field, and any companion stars. Each nebula is unique. Each one tells a different story. The start of planetary nebula creation marks the end of the star's active life. From here, it's just a slow fade, the gas that glows in the darkness. The gas in a planetary nebula glows because it's ionized. Ultraviolet light from the central white dwarf strips, electrons from atoms. When those electrons recombine with atoms, they emit light. Each element emits light at specific wavelengths. Hydrogen emits red light at 656 nanometers. Oxygen emits green light at 501 nanometers. These emission lines create the colors we see in planetary nebulae. The gas is incredibly thin by Earth standards. It's almost a vacuum, but it's illuminated, so it glows. And because space is dark, even faint glowing gas is visible. The patterns in the gas reveal the history of the star's mass loss. Shells, rings, and jets show how the material was ejected. Some nebulae have multiple shells, evidence of different episodes of mass loss. Others have fast-moving jets, created by magnetic fields or companion stars. The gas that glows in the darkness is the star's legacy. It's what remains after a lifetime of fusion, and it's beautiful. A final work of art, painted in light. The dust that will form new worlds. Along with gas, planetary nebulae contain dust, tiny grains of solid material, carbon dust. If the star was carbon-rich, silicate dust. If it was oxygen-rich, this dust is created in the star's outer atmosphere during the red giant phase. As the material cools, atoms condense into solid grains. The dust is incredibly important. It's the raw material for planets. In the interstellar medium, dust provides surfaces where molecules can form. It also helps cool the gas, allowing it to collapse and form new stars. When new stars form, the dust coalesces into planets and moons. Some of the dust in our solar system came from planetary nebulae, grains of stardust, carried through space, incorporated into the disk that formed the sun and planets. You can find these grains in meteorites, presolar grains, they're called. Dust that predates the solar system. Dust that came from a star that died billions of years ago. The dust that will form new worlds connects generations of stars. It's the cycle of stellar life and death, and it's how the universe recycles itself. The cycle of life and death in stars. Stars are born from clouds of gas and dust. They shine for billions of years, and then they die, returning their material to space. That material becomes part of new clouds, new stars, new planets. It's a cycle, life and death, birth and rebirth. Red giants play a crucial role in this cycle. They're the stage where stars create heavy elements, and they're the stage where stars shed their outer layers, returning that material to the galaxy. Without red giants, the interstellar medium would be depleted. All the gas and dust would be locked up in stars and stellar remnants. But red giants give it back. They enrich the galaxy. They make it possible for new generations of stars to have heavier elements. and they make it possible for planets to form, for life to arise. The cycle of life and death in stars is fundamental to the universe. It's how complexity develops, how the universe evolves from simple to intricate, and it's beautiful. A reminder that nothing is truly lost. Everything is transformed. The red giants that enrich the galaxy. Every red giant is a chemical factory. It takes hydrogen and helium, the simplest elements, and fuses them into carbon, oxygen, and heavier elements. When the star dies, those elements are released. They mix into the interstellar medium. They become part of new stars, and with each generation, the galaxy becomes richer in heavy elements. Astronomers call these heavy elements metals, even though many of them aren't metals in the chemical sense. The amount of metals in a star tells us about its history. Old stars have very few metals. They formed early in the galaxy's history, when there hadn't been many supernovae or red giants yet. Young stars have more metals. They formed recently, from material enriched by previous generations. Our Sun is a relatively metal-rich star. It formed from material that had been processed through multiple generations of stars. The red giants that enrich the galaxy are responsible for the diversity of the universe, for planets, for life, for us. Without them, the cosmos would be a simpler, emptier place. The carbon that becomes the building block of life. Carbon is essential for life as we know it. Every living thing on Earth is based on carbon chemistry. Carbon atoms can bond with 4 other atoms, creating complex molecules, proteins, DNA, sugars, fats, all built on carbon backbones. And where does carbon come from? Red giants. Specifically, the triple alpha process in their cores. Without red giants, there would be no carbon. At least, not in any significant amount. There might be trace amounts produced in other reactions, but the bulk of the carbon in the universe comes from helium fusion in red giants. That carbon is released when the star dies. It drifts through space, eventually becoming part of new stars and planets. On Earth, carbon is the 4th most abundant element. It's in the air we breathe, the food we eat, our bodies, and every atom of it was created inside a star, probably a red giant, probably billions of years ago. The carbon that becomes the building block of life connects us to the stars. We are quite literally made of stardust. The stardust that becomes us. It's not just carbon. Every element in your body, except hydrogen, was created in a star. The oxygen in water, the calcium in your bones, the iron in your blood, all forged in stellar cores. Most of these elements were created in red giants, or supernovae, and when those stars died, the elements were released. They drifted through the galaxy for millions or billions of years. Eventually, they became part of the cloud that formed our solar system. They condensed into the sun, the planets, and the moons. And on Earth, they became part of the rocks, the oceans, and living things. You are made of stardust. It's not a metaphor. It's literal. The atoms in your body have been on a cosmic journey. They've been inside stars. They've traveled through interstellar space. They've been part of nebulae and planets and oceans. And now, they're part of you. The stardust that becomes us is a profound connection. It ties us to the universe, to the stars, to the cycles of creation and destruction that have been going on for billions of years. The legacy of every red giant. Every red giant leaves a legacy, not in the form of planets or moons, but in the form of elements: carbon, oxygen, nitrogen. These elements are scattered into space when the star dies. They become part of the interstellar medium. They enrich the galaxy, and they make future generations of stars more interesting. The legacy of a red giant is written in the chemistry of everything that comes after, in the spectra of young stars, in the composition of planets, in the molecules that make life possible. Red giants are stellar elders. They've lived long lives. They've seen billions of years pass, And when they die, they give back. They return what they've created. They enrich the cosmos. That's their legacy, not immortality, not physical survival, but contribution, enrichment, a gift to the future. The legacy of every red giant is a reminder that our actions matter, that what we create, what we give back, is how we're remembered. Even stars understand that. The examples we see in the sky. Red giants are common in the night sky. If you know where to look, you can spot them easily. They're the bright orange-red stars scattered among the white and blue ones. Some are famous, household names, at least among stargazers. Betelgeuse in Orion, Antares in Scorpius, Arcturus in Boötus, Aldebaran in Taurus. Each one is a red giant or supergiant. Each one is a star in its final stages. When you look at a red giant, you're seeing a star that's older than our sun, a star that's already exhausted its core hydrogen, a star that's transformed into something huge and luminous. These stars are close enough that we can study them in detail. We can measure their temperatures, sizes, and compositions. We can watch them change over time. They're laboratories for stellar physics, examples of what every sun-like star will eventually become. The examples we see in the sky are beautiful, but they're also educational. They teach us about stellar evolution, about the future, and about ourselves. The famous star Betelgeuse is one of the most famous stars in the sky. It's the bright orange-red star in Orion's shoulder. You can see it easily on winter nights. It's impossible to miss. Betelgeuse is a red supergiant. It's much more massive than the Sun, about 15 to 20 solar masses, and it's enormous. If you placed Betelgeuse at the center of our solar system, its surface would extend beyond the orbit of Jupiter. The star is variable. Its brightness changes over time. Sometimes, it's one of the brightest stars in the sky. Other times, it dims noticeably. In 2019 and 2020, Betelgeuse dimmed dramatically. For a while, astronomers thought it might be about to explode as a supernova, but the dimming was caused by dust. Material ejected from the star's surface blocked some of its light. Betelgeuse will explode someday. It's near the end of its life. When it does, it will be one of the most spectacular events in human history. A supernova visible during the day. But that might not happen for thousands of years, or it might happen tomorrow. We don't know. For now, Betelgeuse shines, a red giant in its final days. The red shoulder of Orion. In the constellation Orion, the hunter, Betelgeuse marks his right shoulder. It's one of the three brightest stars in the constellation. The other two are Rigel, a blue supergiant at his left foot, and Bellatrix, a blue giant at his left shoulder. The contrast is striking, blue and red, hot and cool, young and old. Betelgeuse's red color is immediately apparent, even to the naked eye. It stands out against the white and blue stars around it. The color tells you it's cool, at least by stellar standards. Its surface temperature is only about 3,500 Kelvin. Compare that to Rigel, which is over 11,000 Kelvin. Betelgeuse's red glow has made it a favorite among stargazers for millennia. Ancient cultures noticed it. They gave it names. The Egyptians associated it with Osiris. The Arabs called it Yad al-Jaza, meaning the hand of the central one. We know it as Betelgeuse, though the exact etymology is debated. The red shoulder of Orion is a landmark in the winter sky, and a reminder that not all stars are young and hot. The variability of its light. Betelgeuse doesn't shine with constant brightness. It's a variable star. Its light fluctuates over multiple cycles. The primary cycle is about 420 days. During this cycle, the star expands and contracts. As it expands, it cools and dims. As it contracts, it heats up and brightens. There's also a longer cycle, about 6 years. The cause of this longer cycle isn't fully understood. It might be related to convection in the star's outer layers, or it might be caused by pulsations of different layers. The variability makes Betelgeuse fascinating to observe. The evidence that it's nearing its end. Betelgeuse is dying. Well, dying in stellar terms. It's near the end of its life. It's already fused hydrogen. It's fused helium. It's likely fusing heavier elements right now. Carbon, oxygen, silicon. It's building an iron core, and when that core becomes too massive, it will collapse. The star will explode in a supernova. The evidence is in its behavior. The variability, the mass loss, the dust production. These are all signs of a star in its final stages. Betelgeuse is shedding mass at an enormous rate. It's losing about 1 solar mass every 10,000 years. That's much faster than typical red giants. The star is also surrounded by a complex nebula, shells and arcs of ejected material, evidence of past episodes of mass loss. We don't know exactly when Betelgeuse will explode. It could be soon, in astronomical terms, within the next 100,000 years. Or it could be much sooner, tomorrow, next year. We just don't know. But when it does explode, it will be spectacular, and the evidence suggests it's nearing that end. The countdown has begun. The Antares star in Scorpius. Antares is another famous red supergiant. It's the brightest star in the constellation Scorpius, marking the scorpion's heart. The name Antares comes from Greek, meaning rival of Mars. It was named that because of its red color similar to the planet Mars. When Mars and Antares appear close in the sky, they're almost indistinguishable in color, but Antares is much brighter. Antares is enormous. Its radius is about 700 times that of the Sun. If you placed it at the center of our solar system, its surface would extend beyond the orbit of Mars. Like Betelgeuse, Antares is a variable star. Its brightness fluctuates slightly over time, and it's surrounded by a nebula, material ejected from the star's outer layers. Antares also has a companion star, a blue-white star that orbits Antares every 900 years or so. The contrast between the two stars is stunning. Red and blue, cool and hot, giant and normal. Antares is one of the most luminous stars visible to the naked eye. It shines with the light of tens of thousands of suns, and it's visible from most of the Earth, the rival of Mars in the night sky. The name Antares is fitting. When Mars passes through Scorpius, the two objects appear similar. Both are red, both are bright. To the ancients, they might have seemed like rivals, competing for attention in the sky. But there's no real rivalry. Mars is a planet, a small world reflecting sunlight. Antares is a supergiant star, producing its own light through fusion. Mars is about 225 million kilometers from Earth at its closest. Antares is about 550 light-years away. That's about 5 quadrillion kilometers. Antares is a supergiant star, producing its own there. The fact that Antares is visible at all from that distance is a testament to its luminosity. The red color of both objects comes from different causes. Mars is red because of iron oxide dust on its surface. Antares is red because it's cool. Its surface temperature is about 3,500 Kelvin. The rivalry between Antares and Mars is a reminder that appearances can be deceiving. Two red dots in the sky, but one is a nearby world. The other is a distant dying star. Both beautiful, both worthy of attention, but very different in nature. The giant that dwarfs our sun, comparing Antares to the sun, is almost absurd. The sun is a yellow dwarf, small, stable, middle-aged. Antares is a red supergiant, massive, unstable, elderly. If you could place them side by side, the sun would be a tiny dot next to Antares. Antares' radius is about 700 times larger. Its volume is about 350 million times larger. You could fit 350 million suns inside Antares, and yet, despite its size, Antares is only about 15 to 18 times more massive than the Sun. How is that possible? Because Antares is incredibly diffuse. Its outer layers are almost a vacuum. The density is so low that if you could stand in Antares' atmosphere, you'd barely notice any material around you. Antares dwarfs the Sun in size and luminosity. It shines with the power of about 75,000 suns, but it's nearing the end. It will explode as a supernova relatively soon. In astronomical terms, the giant that dwarfs our Sun is a humbling sight, a reminder of the diversity of stars and of how small and ordinary our Sun really is. The brightest red giants ever seen. Some red giants are brighter than others, much brighter. The most luminous red giants are called supergiants. They're massive stars, 10 to 40 times the mass of the Sun, and they're incredibly bright. Betelgeuse and Antares are supergiants. But there are others. Mu Cephei, also known as Herschel's garnet star, VV Cephei, one of the largest stars known. Ui Scuti, once thought to be the largest star in the galaxy. These stars shine with the light of hundreds of thousands of suns. They're visible across the galaxy, and if they were placed at the center of our solar system, they would swallow not just the inner planets, but the outer ones too. The brightest red giants ever seen are at the extreme end of stellar evolution. They're massive enough to fuse elements all the way to iron, and they'll end their lives in spectacular supernovae. For now, they glow, crimson beacons in the darkness, dying stars that outshine entire regions of the galaxy. The supergiants beyond comparison. Red supergiants are in a league of their own. They're not just larger versions of normal red giants. They're fundamentally different, more massive, more luminous, more unstable, and they evolve much faster. A star like the Sun will spend billions of years on the main sequence, then a few 100 million years as a red giant. But a red supergiant might only spend a few million years in that phase. Their lives are short and intense. They burn through their fuel quickly, and they end violently. These stars are so large that they defy comprehension. If you replace the Sun with a red supergiant, like VY Canis Majoris, the star's surface would extend beyond the orbit of Saturn. The planets would be inside the star. The supergiants, beyond comparison, are extreme objects. They push the limits of what's possible for a star. They're unstable, pulsating, shedding mass. They're surrounded by clouds of dust and gas. And they're beautiful, terrifying in their scale, but beautiful nonetheless. The hypergiant VY Canis Majoris. VI Canis Major is one of the largest stars known. It's a red hypergiant, even more extreme than a supergiant. Its radius is uncertain, but estimates put it at about 1,400 to 1,500 solar radii. That's large enough to reach past the orbit of Jupiter, if placed at the center of our solar system. VA Canis Majoris is incredibly luminous. It shines with the light of about 270,000 suns, and it's losing mass at a prodigious rate. The star is surrounded by a complex nebula of ejected material, arcs, knots, and filaments of gas and dust. This nebula has been created by episodes of mass loss over the past few thousand years. The star is clearly unstable. It's pulsating, shedding its outer layers. It's in the final stages of its life. VA Canis Majoris will likely explode as a supernova within the next 100,000 years, maybe sooner. When it does, it will be one of the most energetic events in the galaxy. For now, it's a hypergiant, a star so large, so luminous, that it seems almost impossible. A reminder that the universe can create objects beyond our wildest imagination. VA Canis Majoris is extreme, unprecedented, and utterly fascinating. The stars large enough to swallow orbits. When we talk about the largest red giants and supergiants, we often compare them to our solar system. If you placed Betelgeuse at the Sun's position, It would swallow Mercury, Venus, Earth, and Mars. If you placed Antares there, it would reach past Mars. Vi Canis Major would swallow everything out to Jupiter. These comparisons help us grasp the scale, but they're still difficult to truly comprehend. Imagine standing on a planet orbiting one of these giants. You wouldn't see a sun, you'd see a wall of red light filling half the sky, the light that travels hundreds of years to reach us. When you look at a red giant, you're seeing the past. The light left that star years, decades, or even centuries ago. Betelgeuse is about 550 light years away. The light you see tonight left the star around 1475, before Columbus sailed to America. Antares is about 550 light years away as well. Similar distance, similar time frame. Vi Canis Majoris is about 3,800 light years away. The light you see left the star around 1800 BC, before the Bronze Age ended. This time delay means that if a red giant explodes as a supernova, we won't see it immediately. We'll see it years or centuries later, when the light finally reaches us. Betelgeuse might have already exploded. The light from that explosion might be traveling toward us right now. We won't know until it arrives. The light that travels hundreds of years to reach us is a connection across time, a message from the past. When you look at red giants, you're not seeing them as they are, you're seeing them as they were. The glow that tells a story of change. Every red giant has a story, a history of fusion, expansion, and transformation. And that story is written in the light it emits. The color tells us about temperature. The brightness tells us about size and luminosity. The spectrum tells us about composition. By analyzing the light from red giants, astronomers can determine what elements are present in the star's atmosphere. They can measure the star's temperature, pressure, and density. They can track changes over time. Some red giants show emission lines in their spectra. These lines indicate material being ejected from the star, mass loss in action. Others show absorption lines that shift back and forth, evidence of pulsation. The star is expanding and contracting. The glow that tells a story of change is more than just beautiful. It's informative. It's a data stream, a way for the star to communicate across the vast distances of space, and astronomers are learning to read that language, to understand what the star is telling us, the spectra that reveal their secrets. Spectroscopy is one of the most powerful tools in astronomy. It allows us to analyze the light from stars and determine their properties. When you pass starlight through a prism or diffraction grating, it spreads out into a spectrum, a rainbow of colors. But the spectrum isn't smooth. It's crossed by dark lines. These are absorption lines, caused by elements in the star's atmosphere, absorbing specific wavelengths of light. Each element creates a unique pattern of lines. Hydrogen has one pattern, helium has another, carbon, oxygen, nitrogen, all have their own signatures. By studying these lines, astronomers can determine what elements are present in the star and in what quantities. Red giants have distinctive spectra. They show strong absorption lines from molecules like titanium oxide and carbon monoxide. These molecules can only form in cool atmospheres. They're a signature of red giants. The spectra that reveal their secrets are like fingerprints. Each star is unique, and each spectrum tells a story. The absorption lines of cool gases. The atmospheres of red giants are cool. Cool enough for molecules to form. On hotter stars like the sun, molecules are torn apart by the intense heat. But on red giants, with surface temperatures around 3,000 to 4,000 Kelvin, molecules can survive. These molecules create absorption lines in the star's spectrum. Titanium oxide, or TO, is particularly prominent in oxygen-rich red giants. It creates bands of absorption in the red and near-infrared. Carbon monoxide Colorado creates absorption in the infrared. These molecular bands are diagnostic. If you see strong TO absorption, you know you're looking at a cool, oxygen-rich star. If you see strong carbon features, you're looking at a carbon star. The absorption lines of cool gases are windows into the star's chemistry. They tell us what elements are present, how they're combined, and what's happening in the star's outer layers. They're a record of the star's evolution, of the elements it's created, and of the processes shaping its atmosphere. The chemistry of a red giant's atmosphere. The atmosphere of a red giant is a chemical laboratory. Elements created in the core through fusion are dredged up to the surface. Carbon and oxygen, products of helium burning, appear in the atmosphere. Nitrogen, created through the CNO cycle, is also present. The chemistry depends on the ratio of carbon to oxygen. If there's more oxygen than carbon, the oxygen combines with carbon to form carbon monoxide. The leftover oxygen then combines with other elements, forming compounds like titanium oxide and water vapor. These are oxygen-rich red giants, or M-type stars. If there's more carbon than oxygen, all the oxygen is locked up in carbon monoxide. The leftover carbon forms other molecules like carbon chains and polyatomic carbon compounds. These are carbon stars, or C-type stars. The chemistry of a red giant's atmosphere determines its color, its spectrum, and the dust it produces. It's a consequence of what's happening deep in the star's core, a reflection of its evolutionary state. The molecules that form in the cold layers. In the cool outer layers of red giants, molecules can form, not just simple diatomic molecules like carbon monoxide, but complex molecules, polycyclic aromatic hydrocarbons, or PAH. These are ring-shaped carbon molecules, similar to benzene. They're common in carbon-rich red giants. Water vapor forms in oxygen-rich stars. So does silicon monoxide, which can condense into dust grains. Even more complex molecules have been detected. Acetylene, cyanide, formaldehyde. These molecules form through chemistry in the star's atmosphere. They're built from the elements created through fusion, and they're precursors to even more complex chemistry. Some of these molecules will survive the star's death. They'll be incorporated into the interstellar medium, and eventually, they might become part of new planetary systems. The molecules that form in the cold layers of red giants are the seeds of complexity. They're the beginning of organic chemistry, the first steps toward the molecules that billions of years later might contribute to life. The carbon stars rich in dust and smoke. Carbon stars are a special type of red giant. They're stars where the carbon abundance exceeds oxygen. This happens when the products of helium burning are mixed to the surface. Carbon-rich material from the core is dredged up into the atmosphere. The result is a star with a very different chemistry. Instead of oxygen compounds, you get carbon compounds, and carbon is sticky. It likes to form chains, rings, and solids. Carbon stars are surrounded by thick clouds of carbon dust, soot, essentially smoke from a stellar fire. These dust clouds block visible light, making the star appear very red, or even invisible in visible wavelengths. But in infrared, carbon stars are bright. The dust absorbs visible light and re-emits it as infrared. Carbon stars are important contributors to the interstellar medium. They produce and distribute carbon dust throughout the galaxy. That dust becomes part of new stars and planets, and it's essential for the formation of terrestrial planets like Earth. Carbon stars rich in dust and smoke are stellar foundries, creating the building blocks of worlds. The stars that shine in infrared. Red giants are cool, and cool objects emit most of their radiation in the infrared. While we can see red giants with our eyes, we're only seeing a fraction of their light. The majority is in the infrared, invisible to us. Infrared telescopes reveal the true brightness of red giants. They also reveal structures that are hidden in visible light: dust shells, circumstellar envelopes, mass loss. All of these features are brightest in the infrared. Astronomers use infrared observations to study red giants in detail. They can measure the temperature distribution across the star's surface. They can track the flow of material in stellar winds, and they can observe the formation of dust. The stars that shine in infrared are telling us things we couldn't learn from visible light alone. They're revealing their secrets, showing us their structure, and helping us understand the processes that govern their final days. Infrared astronomy has revolutionized our study of red giants, and it continues to provide new insights. The observation of their mass loss. One of the defining features of red giants is mass loss. They're constantly shedding material into space, and we can observe this process. Astronomers use several techniques. They can measure the expansion of circumstellar shells. They can observe the motion of material in stellar winds, and they can detect the dust and gas around the star. Spectroscopy is particularly useful. Emission lines in the spectrum indicate material moving away from the star. The Doppler shift of these lines tells us how fast the material is moving, and the strength of the lines tells us how much material is being lost. Mass loss rates vary. For a typical red giant, it might be a millionth of a solar mass per year. For a red supergiant, it can be much higher, 1,000th or even 100th of a solar mass per year. These are enormous rates. The observation of their mass loss has shown us that red giants don't just sit there. They're active, dynamic, constantly changing, and they're returning material to the galaxy at a significant rate. The clouds of material around them. Many red giants are surrounded by clouds of material, circumstellar envelopes, formed from mass loss over thousands or millions of years. These clouds are complex. They have shells, rings, and irregular structures. The complexity tells us about the history of mass loss. Spherical shells indicate steady, isotropic mass loss. Rings suggest episodic mass loss, and irregular structures hint at asymmetry, perhaps caused by rotation, magnetic fields, or companion stars. The clouds are mostly gas, but they also contain dust. The dust scatters and absorbs light, making the clouds visible. In some cases, the clouds are so thick that they completely obscure the star. We can only see it in infrared. The clouds of material around red giants are laboratories for studying stellar winds. They preserve a record of the star's recent history, and they show us how material is transported from the star to the interstellar medium. They're the interface between the dying star and the galaxy, the stellar winds that feed the cosmos. Stellar winds from red giants are a major source of material for the interstellar medium. Every red giant is pumping gas and dust into space, and there are millions of red giants in the galaxy. The cumulative effect is significant. Stellar winds enrich the interstellar medium with heavy elements: carbon, oxygen, nitrogen, elements created through fusion in the star's core. These elements mix with the existing gas and dust. They increase the metallicity of the medium, and they make it possible for new stars to have planets. Rocky planets, like Earth, require heavy elements: silicon, iron, magnesium. These elements come from stellar winds and supernovae. The stellar winds that feed the cosmos are a form of stellar recycling. The galaxy is a closed system, more or less. Material isn't created or destroyed. It's just transformed and redistributed. Stars gather material from the interstellar medium. They process it through fusion, and they return it, enriched with new elements. The cycle continues, and the galaxy evolves. The pressure of radiation on dust. Stellar winds from red giants are driven by radiation pressure. Light carries momentum, and when light is absorbed by dust particles in the star's atmosphere, it transfers that momentum. The dust particles are pushed outward, and they drag gas with them. This is a very efficient process. A single photon doesn't carry much momentum, but red giants emit enormous numbers of photons, and the dust particles absorb many of them. The cumulative effect is a strong outward force. The pressure of radiation on dust is strongest in cool, dusty atmospheres, which is exactly what red giants have. As material flows outward, it cools, more dust forms, and the radiation pressure increases. It's a self-reinforcing process. The result is a strong stellar wind, material flowing away from the star at speeds of tens of kilometers per second. Over time, this wind strips away the star's outer layers. The envelope is shed, and the core is exposed. The pressure of radiation on dust is what makes planetary nebulae possible. It's the mechanism that transforms a red giant into a white dwarf. The creation of planetary nebulae. Planetary nebulae are one of the most beautiful phenomena in astronomy. They're glowing shells of gas and dust, illuminated by a hot central star, and they're created during the final stages of red giant evolution. As the star loses mass through stellar winds, a shell of material accumulates around it. When the star exhausts its fuel and sheds its envelope, the hot core is exposed. This core is a white dwarf with a surface temperature of 30,000 to 100,000 Kelvin. The ultraviolet light from the white dwarf ionizes the surrounding shell, and the ionized gas glows. The creation of planetary nebulae is rapid. Once the envelope is shed, the nebula becomes visible within a few hundred years. It remains bright for about 10,000 to 20,000 years. Then it disperses. The gas and dust mix with the interstellar medium, and the white dwarf is left alone, cooling slowly. Planetary nebulae are the signposts of stellar death. They mark the transition from red giant to white dwarf, and they're among the most photogenic objects in the galaxy. The final shedding of a star's skin. The moment a red giant sheds its envelope is the moment of transformation. The star has been losing mass for millions of years, but the final shedding happens quickly. In a few thousand years, the remaining envelope is blown away. What's left is the core, hot, dense, and naked. This is a white dwarf. The final shedding is driven by the star's increasing luminosity and pulsations. As the envelope becomes less and less massive, it becomes more weakly bound. Eventually, it's blown away entirely. The process might be assisted by companion stars. Many planetary nebulae are asymmetric, suggesting the presence of a binary companion. The companion's gravity shapes the outflow, creating jets and lobes. The final shedding of a star's skin is both an ending and a beginning. It's the end of the star's life as a fusion-powered object, but it's the beginning of its life as a white dwarf, and it's the creation of a planetary nebula, a final burst of beauty before the long, slow fade. The white dwarf left behind. After a red giant sheds its envelope, what remains is the core. This is a white dwarf, a stellar remnant about the size of Earth, but with about half the mass of the Sun. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons. The density is so high that the electrons are degenerate, creating a pressure that supports the star against gravity. White dwarfs don't fuse. They have no internal energy source. They're just hot remnants, cooling slowly over billions of years. When a white dwarf first forms, it's extremely hot. Its surface temperature can exceed 100,000 Kelvin. It glows white or blue-white, but over time, it cools, it fades. Eventually, after trillions of years, it will become a black dwarf, a cold, dark cinder. Though the universe isn't old enough for any black dwarfs to exist yet, the white dwarf left behind is the ultimate fate of stars like the Sun. It's what remains when all the fuel is exhausted, when all the light has been shed, a quiet ending to a long life. The cooling remnant of a once giant star. A white dwarf is a cooling remnant. It's no longer generating energy. It's just radiating away the heat left over from its previous life. The cooling process is slow, very slow. A white dwarf starts at temperatures of 100,000 Kelvin or more. Over billions of years, it cools to 10,000 Kelvin, still hot enough to glow white. Over tens of billions of years, it cools to a few thousand Kelvin, now glowing red. And over trillions of years, it cools to near absolute zero, becoming a black dwarf. The cooling is predictable. It follows well-understood physics, and that makes white dwarfs useful as cosmic clocks. By measuring a white dwarf's temperature, we can estimate how long it's been cooling, and that tells us how old it is. The oldest white dwarfs in the galaxy have been cooling for billions of years. They're some of the oldest objects we can observe. The cooling remnant of a once giant star is a fossil, a relic from the early days of the galaxy, and a glimpse into the future of our own sun. The slow fade into cosmic silence. The end of a white dwarf is a slow fade. It cools, it dims, and eventually it becomes invisible. There's no drama, no explosion, no final burst of light, just a gradual dimming, a slow fade into cosmic silence. It's a quiet ending, but it's also dignified. The star lived for billions of years. It shone brightly. It created elements. It enriched the galaxy. And now, its work is done. It fades away, leaving behind only its contribution. The elements it created, the light it emitted, the planets that might still orbit it. The slow fade into cosmic silence is the fate of most stars. Not all stars explode. Not all end in supernovae. Most just fade, quietly, peacefully. And perhaps there's beauty in that, in the quiet endings, in the stars that don't demand attention, but simply do their work and then rest. The slow fade is a reminder that not all endings are catastrophic. Some are gentle, and that's okay. The journey from red giant to white dwarf. The journey from red giant to white dwarf is the final chapter in the life of a sun-like star. It begins with the exhaustion of core hydrogen. The star expands, becomes a red giant. It fuses helium in its core, creating carbon and oxygen. It loses mass through stellar winds. Eventually, it sheds its envelope, creating a planetary nebula, and at the center, the white dwarf remains. The journey takes hundreds of millions of years. It's not quick, but it's inevitable. Every star, like the sun, will follow this path. The journey is well understood. We've observed stars at every stage. We've modeled the physics. We've measured the timescales, and we've confirmed that our predictions match reality. The journey from red giant to white dwarf is a story of transformation, from a stable, fusion-powered star to a cooling remnant, from activity to silence. It's the natural progression, the way stars age, and in its own way, it's beautiful. The timeline of stellar death. The timeline of stellar death depends on the star's mass. For a star like the sun, one solar mass, the timeline looks like this. Main sequence, 10 billion years. Red giant phase, a few 100 million years. Helium burning, about 100 million years. Asymptotic giant branch, a few million years. Planetary nebula, 10,000 to 20,000 years. White dwarf cooling, trillions of years. For more massive stars, the timeline is shorter. A 10 solar mass star might spend only 20 million years on the main sequence. Its red giant phase might last only 1 million years, and it ends in a supernova, not a planetary nebula. Less massive stars live even longer. A 0.5 solar mass red dwarf might burn for 100 billion years or more. The universe isn't old enough for any red dwarfs to have died yet. The timeline of stellar death is dictated by physics, by the star's mass, composition, and the efficiency of fusion. It's predictable, measurable, and it tells us the story of how stars live and die, the many paths, depending on mass. Not all stars follow the same path. Mass determines destiny. Low-mass stars, less than about 0.5 solar masses, burn slowly. They'll live for hundreds of billions of years. When they finally die, They'll skip the red giant phase entirely and become white dwarfs directly. Sun-like stars, 0.5 to 8 solar masses, become red giants. They fuse helium, they shed their envelopes, and they become white dwarfs. Massive stars, 8 to 25 solar masses or more, become red supergiants. They fuse elements all the way to iron, and they end in supernovae, leaving behind neutron stars or black holes. The most massive stars, above 100 solar masses, might skip the red supergiant phase. They might become blue supergiants, or Wolf-Rayet stars, and they end in the most energetic supernovae, hypernovae. The many paths depending on mass show us the diversity of stellar evolution. Stars aren't all the same. They don't all end the same way. And that diversity is what makes the universe interesting. The stars that collapse further still. Some stars don't stop at the white dwarf stage. If a white dwarf is in a binary system and accretes material from a companion, it can gain mass. If it gains enough mass, it can exceed the Chandrasekhar limit, about 1.4 solar masses. When that happens, the white dwarf becomes unstable. Electron degeneracy pressure can no longer support it, and it collapses. For white dwarfs, that collapse triggers a runaway fusion reaction, a type Ia supernova. The entire star is destroyed. For more massive stars, the collapse is different. The iron core collapses directly. In less than a second, it shrinks from thousands of kilometers to tens of kilometers. Protons and electrons are crushed together, forming neutrons. The result is a neutron star. If the core is massive enough, not even neutron degeneracy pressure can stop the collapse. It becomes a black hole. The stars that collapse further still are the most extreme objects in the universe, and they teach us about physics at its limits. The supergiants that end in explosion. Red supergiants don't fade quietly. They explode. When a red supergiant exhausts its fuel, its iron core collapses. The collapse is catastrophic. In less than a second, the core goes from the size of Earth to the size of a city. The collapse releases gravitational energy, an enormous amount of energy. Some of that energy goes into creating a shock wave. The shock wave travels outward through the star's layers. When it reaches the surface, the star explodes. This is a Type II supernova. The explosion is one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy. The explosion scatters the star's outer layers into space. Elements created in the core, and elements created during the explosion itself, are distributed throughout the galaxy. The supergiants that end in explosion are cosmic catastrophes, but they're also cosmic benefactors. They create and distribute the heaviest elements: gold, platinum, uranium, elements that can only be created in the extreme conditions of a supernova. The elements scattered across the galaxy, supernovae, are the primary source of heavy elements in the galaxy. Elements heavier than iron can't be created through normal fusion. They require neutron capture, and that happens during supernovae. As the shock wave passes through the star's layers, neutrons are captured by atomic nuclei. This creates heavier and heavier elements. The raw process, or rapid neutron capture process, it creates elements like gold, platinum, and uranium. These elements are scattered across the galaxy by the supernovae explosion. They mix with the interstellar medium, and they're incorporated into new stars and planets. Every atom of gold on Earth was created in a supernova. So was every atom of uranium. These elements are literally star stuff, forged in the most violent events in the cosmos. The elements scattered across the galaxy by supernova are a testament to the power of stellar explosions and to the role stars play in creating the chemical diversity of the universe. The light curves that record their passing. When a supernova explodes, it brightens dramatically. Over a few days, it can increase in brightness by a factor of 1 billion. Then it fades. The rise and fall of brightness is called a light curve, and it's a record of the supernova's passing. Different types of supernovae have different light curves. Type Ia supernovae, from white dwarfs, have a characteristic shape. They rise quickly, peak, then fade steadily. Type Ia supernovae, from red supergiants, have a different shape. They have a plateau phase where the brightness stays relatively constant for weeks. By studying light curves, astronomers can determine what type of supernova occurred, how much energy was released, and how the explosion evolved over time. Light curves are also used to measure distances. Type Ia supernovae have a well-defined peak brightness. By measuring how bright they appear from Earth, we can calculate how far away they are. This has been used to map the universe and discover that its expansion is accelerating. The light curves that record their passing are more than just data. They're stories. Stories of stars that lived, exploded, and faded. Stories written in light, the dust shells seen by telescopes. Many red giants and supergiants are surrounded by dust shells. These shells are created by mass loss. As material flows away from the star, it cools. Molecules form, and some of those molecules condense into solid grains. Dust. The dust shells are visible in infrared. They absorb visible light from the star and re-emit it as infrared. This creates a characteristic signature, an infrared excess. Telescopes like Spitzer, Herschel, and now James Webb have imaged dust shells around many red giants. The images reveal intricate structures, shells, arcs, spirals. Each structure tells a story about the star's mass loss history. The dust shells seen by telescopes are beautiful, but they're also informative. They tell us how much mass the star has lost, how the material is distributed, and what's happening in the star's outer atmosphere. In Nave Coupe, also tell a story about the star's mass loss history. They're a window into the final stages of stellar evolution, and they show us that even dying stars create beauty. The observations from Hubble and James Webb. The Hubble Space Telescope and the James Webb Space Telescope have revolutionized our understanding of red giants. Hubble, operating in visible and ultraviolet wavelengths, has captured stunning images of planetary nebulae. It's revealed structures that were invisible from ground-based telescopes. Shells, jets, rings, all in exquisite detail. Webb, operating in infrared, is revealing the dust and molecular structures around red giants. It's seeing through the dust, imaging the stars themselves, and it's detecting molecules in their atmospheres that were previously undetectable. Together, these telescopes are providing unprecedented views of stellar evolution. They're showing us how stars lose mass, how dust forms, how planetary nebulae develop. The observations from Hubble and James Webb are transforming our understanding. They're providing data that's confirming our theories, and they're raising new questions. Each new image is a discovery. Each new spectrum is a clue, and we're learning more about red giants than ever before. The study of stellar evolution in real time. Stellar evolution happens on time scales of millions to billions of years. We can't watch a single star evolve, but we can observe many stars at different stages, and from those observations, we can piece together the sequence. It's like reconstructing a human lifetime from snapshots of many people at different ages. You might see a baby, a child, a teenager, an adult, and an elderly person. And from those snapshots, you can infer the progression. The same is true for stars. We observe main sequence stars, red giants, white dwarfs, and we understand the progression. But occasionally, we get to see changes in real time. Betelgeuse's dimming in 2019 to 2020 was one example. We watched the star change over months. It was a glimpse of stellar evolution happening on human timescales. The study of stellar evolution in real time is rare, but when it happens, it's incredibly valuable. It confirms our models, it reveals new processes, and it reminds us that the universe is dynamic, always changing, always evolving. The lessons red giants teach about the universe. Red giants teach us many lessons. They teach us about fusion, about how stars create energy, about how elements are built up from simpler ones. They teach us about stellar structure, about how pressure and gravity balance, about how stars respond to changes in their cores. They teach us about mass loss, about stellar winds, about how material is returned to the galaxy. They teach us about time, about the vast timescales of stellar evolution, about patience and inevitability. They teach us about ourselves, about where we came from, about the fact that we're made of stardust, that the elements in our bodies were created in stars like these. Red giants are teachers. They're laboratories. They're reminders, and they're beautiful. The lessons red giants teach about the universe are fundamental to our understanding of astronomy and to our understanding of our place in the cosmos. The proof that all things transform. Red giants are proof that nothing stays the same forever, not even stars. Stars are born, they live, they age, and they die. But death isn't the end. It's a transformation. The star doesn't vanish. It changes form. It becomes a white dwarf, or a neutron star, or a black hole. Its material is returned to the galaxy, and that material becomes part of new stars, new planets, new life. The cycle continues. Transformation is the fundamental rule of the universe. Nothing is permanent. Everything changes. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes stardust. Stardust becomes us. The proof that all things transform is written in the stars, in their light, in their spectra, in their evolution. Red giants are the elders, showing us that change is natural, that transformation is inevitable, and that endings can be beautiful. The reminder that even stars grow old. Stars seem eternal. They shine for billions of years. They're constants in the night sky. But they're not immortal. They age, just like everything else. They exhaust their fuel. They change. They fade. Red giants are elderly stars. They've lived most of their lives. They've burned through their hydrogen, and they're nearing the end. The reminder that even stars grow old is humbling. If stars can age and die, then nothing lasts forever. Not planets, not galaxies, not even the universe itself. But there's comfort in that. Aging isn't failure. It's natural. It's the progression of life. And in the case of stars, aging is productive. Red giants create elements. They enrich the galaxy. They make life possible. The reminder that even stars grow old teaches us to appreciate the moment, to value what we have while we have it. Because nothing, not even stars, lasts forever. The beauty of light that comes with age. There's a special beauty in the light of red giants. It's not the fierce, blue-white light of young stars. It's softer, warmer, more gentle. Red light is the light of age, of cooling, of slowing down. But it's no less beautiful for it. In some ways, it's more beautiful. There's a depth to it, a richness. The light of a red giant has traveled from a star that's seen billions of years pass, a star that's created elements, that's transformed, that's lived. When you look at a red giant, you're seeing that history, that journey, that transformation. The beauty of light that comes with age is a reminder that beauty isn't just in youth, it's in all stages of life. In the middle years, in the final years. Red giants are beautiful because of their age, not despite it. They glow with a light that can only come from experience, from time, from transformation, and that light is precious. The cosmic truth of impermanence. The universe is impermanent. Nothing lasts forever. Stars are born and die. Galaxies collide and merge. Planets form and are destroyed. Even the universe itself had a beginning and it will have an end. Red giants embody this truth. They're stars in transition, moving from one state to another, changing, evolving, fading. The cosmic truth of impermanence can be uncomfortable. We like to think of things as stable, permanent, but they're not, and that's okay, because impermanence makes things precious. If stars lasted forever, they wouldn't be special. If the universe were eternal and unchanging, it would be boring. Impermanence is what makes moments matter, what makes beauty meaningful. Red giants teach us to embrace impermanence, to accept change, to find beauty in transformation, and to appreciate the moment, because it won't last. And that's what makes it precious. The eternal cycle of death and renewal. But impermanence isn't the end of the story. There's also renewal. Stars die, but their material lives on. It forms new stars, new planets, new life. The cycle continues. Red giants return carbon and oxygen to the galaxy. Those elements become part of new nebulae. New stars form from those nebulae. And those stars might have planets, and those planets might have life. The eternal cycle of death and renewal is the heartbeat of the universe. Stars are born from the ashes of previous stars, and when they die, they seed the next generation. Nothing is truly lost. Everything is transformed, recycled, renewed. Red giants are part of this cycle. They're not just endings, they're also beginnings. Their death makes new life possible. Their light feeds the cosmos. The eternal cycle of death and renewal is a source of hope. It reminds us that endings aren't final, they're transitions, and that even in death, there is the promise of something new, something beautiful, something that carries forward the legacy of what came before.